Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called HI Water, enterprise-wide optimization system for water resources companies. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. HI Water corresponds to the optimization system at the business level, especially oriented to the planning and operation of water resources. It can be used standalone or integrated with HI Power. Hydraulic model. HI Water allows any type of connectivity for the topology of the hydraulic system. Modeling of pump storage plants is included, with detailed modeling of pumping stations. If there are special management rules for water resources, such as exogenous agreements for the management of external demands, these can be included in the modeling. Water systems. Subjective penalties. In the modeling of electrical systems, to plan and schedule the dispatch of plants, the use of subjective penalties has been traditional. This goes back to the beginning of the use of linear models, many of which are still employed, to deal with nonlinear aspects of the real problem. Some examples of the use of this type of artifice are reservoir discharges, to control early discharges from a low productivity chain to a higher productivity chain, whether technical or economic. Management of other priority demands, such as irrigation, aqueduct, minimum flows, flood control. Control of the minimum level of tanks to give reliability to the system. These approaches involve the distortion of the associated dual problem. HI Water allows the user to select the exact modeling, alternative to subjective penalties. The effect on the dispatch of the plants on the penalizing factors of the discharge from the reservoir and the minimum flow, the ecological flow, is presented. The experiments, and their results, were extracted from a report of users of a dispatch model of normal use in the electrical environment, carried out at the end of the last century. For each subjective parameter 3 values were selected, which are reported in the table. The table presents the average values for generation in each case. Given the lack of technical support for the parameters, the results depend on the modeler's decision. Assigning the minimum values maximizes hydroelectric generation, which is consistent since, for 0 values, it is equivalent to not affecting hydroelectric generation. But the quantification of the parameter is not justifiable. On the other hand, maintaining an average flow penalty and maximizing the minimum penalty maximizes thermal generation. The results presented are inconsistent, as a continuous trend would be expected. The quantification of the parameter is not justifiable. When the water stored in a reservoir cannot be controlled, the reservoir discharges are modeled by a channel, which connects to another reservoir or takes the water out of the system. If these relieved or discharged waters are subsequently used in the system to meet the demand for water and/or electricity, a mathematical problem can be posed, when the flow implies a greater efficiency than the use of water resources than by the normal route, since they turn the problem into a disjunctive programming, which requires the use of binary variables to be solved exactly. The traditional way to avoid the mathematical problem is to include penalties in the objective function, which does not solve the problem, since in stochastic programming there may be situations in which spillage occurs, but we do not identify it in the results. HI Water exactly controls discharges from reservoirs and hydroelectric power plants. Water systems. Optimal degenerate solutions. The degeneration of the optimal solution is related to the multiple physical solutions, primal variables, that meet the conditions of optimality and feasibility of the problem. In a normal optimal solution, there is only one solution point to the problem. It is ideal. In the degenerate case, the set of optimal solutions is found in the hyperplane that defines one of the constraints with which it is collinear, or parallel, to the hyperplane of the objective function. In a convex programming problem, these equa-optimal solutions are in a convex set. The solution algorithms find only one point, among the infinite number of points that make up the convex set. In the case of hydroelectric systems, The problem arises when there is an imbalance between the supply and demand that the system serves. Degeneration implies that the use of the water resource of a set of reservoirs, during a given set of periods, is indifferent, since it does not alter the cost of operation, producing the same value for the objective function. Several important problems arise from degeneration. Greater difficulty in solving optimization problems, therefore, greater computational effort. Difficulty in comparing solutions obtained with different algorithms or models, which being the same apparently produce large changes, maintaining in all cases the same value of the objective function. Lack of definition of the dual variables, at the level of individual reservoirs, and problems in the application of regulations, due to multiple remunerations for agents. High water can solve the problem of the lack of definition of dual variables in chains of storages, physical or virtual, that produce degenerate solutions. Degenerate solutions are presented in reservoir networks, either directly connected or through an electrical transmission system. Degeneration occurs when a reservoir can be used interchangeably, or when it can be used in different periods. As the slack in the system increases, the degeneration increases. Degeneracy is not a modeling problem, it is mainly due to the data that causes it. Modeling the water system. According to their efficiency for energy transformation, there are two types of hydroelectric power plants. Fixed loading plants, this is considered an efficiency factor for the plant independent of the head of a reservoir associated with the plant. Plants with variable head, this is considered an efficiency factor for the plant that depends on the head of a reservoir associated with the plant. There are other features to consider, such as whether it has a reservoir or pond, or if it has a bypass. The first case is easily modeled using linear models. The second case leads to complex mathematical modeling, since its consideration results in a nonlinear and non-convex problem, which implies computational difficulties when one wants to have the exact solution of the problem. At high water, the hydroelectric power plant is made up of multiple generation units, which are the ones that convert the water turbine into electrical energy. Each generation unit can be modeled independently. There are multiple types of turbines, the most well-known, Pelton, Francis, and Kaplan. Although their objective is the same, electricity generation, each of them is differentiated by the areas of feasibility of the operation, and the efficiency curves of the transformation of kinetic energy into electricity. These curves are convex, reaching maximum efficiency before 100% of the turbine's capacity. Ignoring this feature in optimization implies an inefficient use of water, since when operating close to the capacity of the turbine, a linear approach will tend to operate the turbine at 100% of its capacity. The hydroelectric generation curve is directly related to the bathymetry of the reservoir. It is generally assumed that it is associated with a convex approximation, which can be represented by a convex envelope. If a convex approximation is used, the problem will be linear and very approximate. For real reservoirs, it is possible that the hydroelectric generation curve has concavities, in which case in a convex approximation there would be areas of overestimation and others of underestimation. The graph presents possible functions that relate the hydraulic generation, GH, with the turbine flow, Q, for different hydraulic heads, H. If the convex Hall, linear approximation, does not coincide exactly with reality, it may be convenient, and/or necessary, to make an adjustment to obtain more accurate results. This will involve the use of binary variables. At high water, the modeling of variable head plant generation is based on the convex hull approach, presented in the paper. A four-dimensional model of hydrogeneration for the short-term hydrothermal dispatch problem considering head and spillage effects. The convex hull corresponds to the discrete minimum envelope, which contains all the points of the hydroelectric generation function, megawatts, depending on the turbine flow rate, cubic meters per second. The approach is based on the discretization of storage and flow from a network of points, for which the hydrogeneration function can be accurately evaluated. Pump storage projects should consider that the pumping flow rate depends on the configuration of the pumps at a station. The pressure, determined by the difference in the level of the upper reservoir, plus the energy losses in the pipeline that grow exponentially with the flow. This combination defines the time for which the water will be pumped, the amount of water pumped, which will define the dynamics of water use in the generating plant. The simplest simulation method is to model the aggregate operation of the pumping station, based on a nonlinear exponential function, which could be approximated by a linearized polyline in parts. This can be feasible in tactical or strategic models. The alternative, perhaps necessary for large plants of this type, is detailed modeling of the operation of the pumping station. The mathematical problem is quite complex, of the MINP type, mixed nonlinear integer programming. Based on High's experience in pipeline projects, High Water includes detailed, convex hull-based modeling of optimal pump station operation. The first step is the decomposition of the problem, generating the convex hull of the entire pumping station. This process involves extracting the pump station model from the monolithic model. With this model, the convex hull will be produced, which will be represented by a mesh of flow pressure points. For each point of the mesh, the problem of optimizing the operation of the pumping station must be solved. Since the product to be pumped is water, which does not dynamically change its characteristics, the process results are stored in a permanent database, for later use in the piping system optimization model. This process can be done offline, prior to the use of the optimization model. The integral model must incorporate the equations that allow working with the convex hull to determine the flow and pressure of the station. High Water can consider is the evaporation of water in the reservoirs, which can be a function of hydroclimatic variables, together with the water level in the reservoir, and evaporation control measures. Synthetic flow generation. For water resources, there are several synthetic generators available. The first can be supported by statistical models of multivariate synthetic generation, such as firing Metalis. This type of model, aimed at preserving the mean, may have limitations when it comes to representing the tails of the probabilistic distribution. The second, commonly used, is based on the extraction of segments, subseries, from the historical series. The theoretical basis of this methodology is: historical series are a sample of a process that has occurred in real life, which is assumed to be stationary and returns to the mean in t years, on a monthly or weekly basis, depending on the frequency of data in the historical series. The historical series preserves the expected value, the cross correlations, lag 0 and lag 1, of all hydroclimatic variables, and the historical series contains extreme events that have occurred, and therefore some of the subseries are linked to these events that preserve the distribution of the tails of the probabilistic distribution. The modeler can choose the historical subseries to use, considering some indicator of criticality, of a lot or a little water. The third, developed by High, is supported by the analysis of ENSO events, the El Niño Southern Oscillation, which has been shown to determine energetic climatological variables, such as water input, wind speed and solar luminosity. The ENSO is a fundamental variable for forecasting events that may occur in the Pacific Bowl countries, but its effect has an impact on a global level. The importance of ENSO events has given rise to a large amount of research, which has multiple models aimed at predicting ENSO events in the short and medium term. The International Research Institute for Climate and Society, IRI, at Columbia University, publishes results obtained with two methodologies to project the ENSO index. Subjective, based on a consensus between analysts from the CPC, Climate Prediction Center, and the IRI. Objective, based on a Bayesian regression model of integration of prediction models, from multiple sources, which determines the weighting factors of each of the available models. Two types of prediction models are used. Dynamic, based on the physical modeling of the dynamics of the process, and statistics, based on empirical evidence of the process. The graphs include the prediction made with each type of model. The black line indicates the weighted prediction using the two types of models. The graph presents the predictions of the models included in the IRI studies and the Bayesian model of forecast consolidation, in the case of statistical models. The High methodology is based on the integration of IRI's ENSO prediction with the observed historical series of climatological variables. The ENOS High model uses an optimization model, the result of which is the convex combination of historical series, which represent the best synthetic scenario generated from the statistical characteristics of the Erie forecast. Flood modeling. To model floods, it is assumed that the water reaches a flood zone downstream of a control point, for example, a reservoir. Flooding is assumed to exist when the flow level is exceeded, which can be carried out in a controlled manner through the flood zone. The flow corresponds to a natural contribution to the flood zone can be rainwater or surface water. In addition to the flow of water from the reservoir, by any of the possibilities, that is, water discharged from the reservoir plus water transferred to other reservoirs, more water from the reservoir to hydroelectric power plants. In addition to water from other flooded areas. Except for water flowing into other flooded areas or leaving the flood system. Two aspects should be considered for modeling flood-related aspects. Modeling of the physical process, and flood costs. The physical flooding process involves coordinating two processes, the monthly dispatch of water resources, with floods occurring within the monthly period, based on characteristics that change from month to month. To achieve the above, the monthly period is divided into two periods. Uncontrolled, during which flooding is inevitable as it is caused by the natural contribution that exceeds the conduction capacity of the canals, natural or built, that cross the flood zone. Controlled, during which it is possible to control flooding, since the natural flow is less than the conduction capacity within the area. It is assumed that flooding generates costs associated with the amount of water that floods an area, here called discharges. Depending on the volume of water that exceeds the capacity of the flooded area, a flood cost with nonlinear characteristics is considered. To this end, the incoming flow is composed of several sections in such a way that the nonlinear features are considered by means of a linearized curve by sections. Each branch of the flood cost curve is delimited to ensure proper representation. Aquifer and Contamination Dispersion Model. High water has a generic mathematical modeling framework for complex water resource systems, which must be optimized based on difference or finite element models. The optimization model is two levels. At the higher level, there is an optimization model associated with strategic and operational decisions that determines the parameters and/or boundary conditions of a finite difference model at the lower level, which represents the complex water resources system. The interaction between the two levels generates information about the gradient of the target function, for decisions associated with the finite difference model. In this way the trajectory to the optimal point is obtained, for an objective function based on these parameters. The approach is applicable to models of displacement in bodies of water, such as groundwater, pollution in rivers, underground flow, lakes, and estuaries. High water is a mathematical model for regional water resources planning. Designed and implemented as a mathematical model of stochastic programming and large-scale optimization, which simulates multi-purpose water resources systems. The model was designed for use in activities of design of water resources networks, medium-term planning of water systems, or short-term trading scheduling. Water resources network models. Optimal design of mesh water supply systems. High water includes a mathematical optimization model for the design and redesign of aqueduct network, and the automatic reconfiguration of the equations, when check valves are activated during operation. The model is of the linear mixed programming type, oriented to work with commercial diameters. Optimal design of radial water supply systems. High water includes a model for the design of radial water supply systems. The model is used for the design, redesign and/or operation of systems including pipelines, tanks and pumping stations. The two models, mesh and radial, can be integrated for hybrid networks. Optimal design of water drainage systems. High water includes a model for the simulation and design of water drainage systems. The optimization model is connected to a simulation model that, using wave kinematic theory, describes the dynamic process of water runoff along the drainage network. The simulation model is used to validate the results of the optimization model. In the event of large differences, The optimization is improved with the corrected maximum flow rates. Flow prediction model. Short-term flow forecasting. High water includes a model for short-term prediction of river flow. The model is based on a state estimation framework using the multi-state Kalman filter methodology, developed by High's chief scientist. Like Albert Einstein, hypothalamus artificial intelligence believes that the mind that opens to a new idea never returns to its original size. Thank you for your attention.